Hello everyone who's watching. Today I'm going to be speaking about using reinforcement learning to design chemical engineering processes. So I'm going to start off with a quick description of what reinforcement learning is and how to think about process synthesis as a reinforcement learning task. Then I'm going to speak about the work I've been doing this year, creating something which I call Distillation Gym, which demonstrates that reinforcement learning can be applied to process synthesis problems through a set of simple distillation train design problems. Then to end off, I'm going to speak about the next step in this work, which is to create Chemical Engineering Gym, which is an all-purpose framework for reinforcement learning problems in process synthesis. And I'm going to speak about how CO-LaN may aid this work. So reinforcement learning is a type of machine learning in which a reinforcement learning agent makes a set of sequential decisions or takes a set of sequential actions in order to maximize an expected reward. Reinforcement learning has recently been made popular through application to board games like chess, as well as computer games like StarCraft. So the way it works is the reinforcement learning agent repeatedly performs a task, which generates experience, which then the agent learns through to improve on the task over time. More specifically, the task is structured as something called a Markov decision process. And the way this works is the agent exists in the environment which is described by a state. The agent then takes an action which causes the environment to transition to a new state, and the agent getting a corresponding reward describing on whether the task is being performed good or bad. This is repeated until the task is done. The task could be done because the agent completed it successfully, or for some other definition of it being done, for example, a maximum number of steps in the environment being reached. So reinforcement learning has been applied to chemical engineering problems. It's been applied to process control as well as optimizing existing processes. However, it has not been applied to process synthesis. We can actually structure process synthesis tasks as a Markov decision process such that the reinforcement learning toolkit becomes available to solve these type of problems. So to describe how this can be done, I'm going to step through an example of a process synthesis task, framing it as a Markov decision process, noting that to do this, the key things we have to do is define along the way states, actions, and then transitions to new states and corresponding rewards. So in the example problem, I'm going to assume that the process only has two compounds that are relevant, A and B, both of which can be bought and sold at some market price. And the property packages for the process simulation of this process have already been defined. So the agent starts off with a blank process flow sheet. So the state would look something like just an array of zeros. Then let's say the first action that the agent takes is to add a stream with 10 moles per second of A, which is available at 25 degrees C and 101 kPa. So now the new state will look like something like a stream table containing just the stream. The corresponding reward could be the raw material cost of 10 moles per second of A converted into an annual amount. So then let's say the next action that the agent takes is to add a Gibbs free energy reactor. The agent specifies that the reactor should be operated at the same conditions as the inlet stream. Then after running the simulation, we can see that the result is 9 moles per second of B being produced, 1 mole per second of A being produced at the same conditions. And let's say in this example that 90 streams with 90% B and 10% A can be sold. So then the reward corresponding to this action could be the revenue generated through selling the product stream with the cost of the new reactor subtracted from it. The new state would now describe this whole new process configuration. So it would look something like a stream table containing both showing the composition and conditions of both the streams, and maybe showing that A is connected to an inlet reactor where B is an unconnected stream, and potentially also the state could include a description of the reactor. So then this can be extended to far more complex actions. The reinforcement learning agent could potentially do anything that a human does within when designing a process within a process simulator. So this can include more units, like adding a distillation column. It could include maybe editing the conditions of a unit or adding a recycle stream. Yeah. So this year I've been working on building Distillation Gym, which is a set of simple reinforcement learning problems in which a distillation train is designed. So the design is simple in the sense that the agent only adds a tree, like the standard tree structure as shown in that picture of distillation of sequential distillation columns, and there are no other units like reactors, and there are no recycle loops. So the user defines a selection of compounds and the starting stream for the process, as well as the necessary property packages to simulate the distillation columns. The user also defines the product definition, which includes the required purity for streams to be sold, as well as the prices that streams can be sold at. So in the next slide, I'm going to quickly go through the Distillation Gym Markov decision process step by step. But on a high level, the agent selects whether or not to separate streams in the process, and then if it decides to separate streams, it has to do the complete column specification for that separation step. Then the reward the agent gets is the revenue of any product streams that the distillation step produces, according to the product stream definition, so whether the stream is above a certain threshold of purity, minus the total annual cost of the additional column, which is calculated using ChemSep. The simulation is done on a unit by unit basis, so just a single unit is actually run in COCO and ChemSep at a time, and then Python is responsible for the rest of the control of the Markov decision process and the agent. So the process starts off with just a single user-defined stream. The agent then has to select whether or not to separate it. Let's say in this example that does choose to separate it. It then has to specify a column operating pressure. This is controlled by a valve before the column. And then it has to specify the number of stages of the column, the reboil ratio, and the reflux ratio. This results in two new streams being produced. Let's say the top stream happens to meet the product definition, then that becomes an outlet to the process. Let's say the bottom stream is still mixed, then the reward given will be the stream's revenue minus the unit's total annual cost. And then, so then the next decision that the agent has to make is whether to separate or not the stream. Let's say it does choose to separate the stream, then again it has to specify the column's complete design. Let's say this is also a product stream, and then finally, let's say the agent decides not to separate this stream here, even though it doesn't meet product specification. So then, if it decides not to separate, it also becomes an outlet stream. And now that there are no available streams left to separate, the episode will be done. So the agent will repeatedly be making a set of decisions that looks like that, and designing better and better, or hopefully designing better and better distillation train configurations over time. So as a demonstration of Distillation Gym, I created two example problems. So how a problem needs to be defined for the Distillation Gym to work is just for the starting stream to be defined and the product definition to be defined. In both cases, I just assumed a 95% purity was enough for the product stream to be sold. And then, the initial starting stream compositions are given on the slide for a benzene, toluene, P-xylene problem and a hydrocarbon containing a mix of hydrocarbons. The agent I used was the soft actor critic agent. I'm not going to describe the details of it here, but they are available in the paper and on my GitHub repo. I did adapt the agent slightly On a very broad level, the agent has two neural networks. One neural network learns the value of a state given the next action that's going to be taken, and the other neural network learns to predict actions that are going to maximize the predicted value of the state given the chosen action. Next I'm going to go through both of these problems, but in both cases the agent was successfully able to learn within the environment to produce better and better distillation column designs. So here are the results from the agent being trained on the benzene, toluene, P-xylene problem. On the left-hand side graph, we can see that the agent's performance improves throughout its training. And we can see that the best designs also improve throughout the training period. The best designs are shown by the peaks of blue in the graph. Then on the right-hand side, we have the best design outcome, which has a much higher total revenue than column cost. To better understand this BFD on the right-hand side, I think the easiest way to see the agent learning is to take samples of the best designs that were produced throughout the training period. So let's step through some of those. So we can see in the early designs, the agent is using far more columns, which results in a higher TAC, and the recovery is lower than the best design. Then throughout the training, the agent designs distillation trains with fewer and fewer columns. With the final design using only 2 columns to produce 3 revenue streams, which has a much higher revenue and lower TAC than the previous designs that I tried. Interestingly enough, I compared this design to the example given on the ChemSep page, and they had a very similar result for the total revenue minus the total annual cost of the columns. So then in the hydrocarbon problem, on the left-hand side graph, we can see that the agent's performance greatly improves throughout its training, and that the best designs, the peaks in the blue on the graph, also improve throughout the training. On the right-hand side of the slide, we can see the best design outcome that the agent was able to do with a much larger revenue than total column cost, and it's able to achieve very high recovery of all of the compounds. So if we compare the best overall design that we saw in the previous slide to one of the best designs that happened early in the training period, we can see that the agent's able to achieve a much higher recovery in the final design compared to earlier, and a much lower total annual cost in the final design compared to earlier designs. So this is the final auto-generated BFD. One thing to note for these auto-generated BFDs is that it puts the valve and the column just in a single block for simplicity. So the key thing to note for both of these problems is that the reinforcement learning agent can learn within these environments, and it improves over time, and it is able to generate better and better process designs, demonstrating that the reinforcement learning approach is possible for process synthesis. So we've seen in Distillation Gym that reinforcement learning can be applied to simple chemical engineering process synthesis tasks, designing chemical engineering processes from scratch. The next step in this work is to create something I call Chemical Engineering Gym, which would be an all-purpose reinforcement learning for process synthesis framework that allows reinforcement learning to be applied to a broad set of process synthesis problems. The key thing to do here would be to extend the action space of the agent to include many more actions. So if one thinks about the actions that a human takes when designing a process within a process simulator, we would want to include all of those actions that are important. So for example, this would include things like allowing the agent to select from a much larger selection of units. So like, for example, also including reactors. The agent should be able to edit the existing process configuration. It should be able to add new streams to the process. It should be able to pick which streams to sell. It would be useful having a big data set of product prices and raw material prices to allow for this. So extending the reinforcement learning approach to more complex domains is where it may have an advantage in comparison to conventional computational techniques for process synthesis. And this is because of the ability of the reinforcement learning toolkit to tackle very open-ended problems. An example of this being the application of reinforcement learning to the StarCraft game. Furthermore, I think that the structuring of process synthesis as a sequential decision-making task is an accurate or more complete description of what process synthesis entails. This is in comparison to more conventional structurings of the process synthesis problem. For example, structuring it as an optimization task of a fixed set of parameters. So if COCO-LaN are interested in aiding this work, the biggest thing they could do would be to add an interface between external programs and process simulator environments that gives the external programs complete control over the process flowsheet. So giving an external program as much functionality as what a user has when interacting with a process flowsheet via a graphical user interface. So currently, external programs are able to do things like edit existing unit parameters, but this is still very limited, and functionality that doesn't currently exist, that could be added, that would be really useful, would be giving external programs the ability to add new units in a process flowsheet, to add new streams in a process flowsheet, to completely manipulate the topology of the process flowsheet, so adding things like recycle streams, deleting units, deleting streams, just really extending all the functionality that the user has in a process flowsheet to what an external program is able to do. And I expect that this would be useful outside of just reinforcement learning for process synthesis. I expect it would be useful for interaction between external programs and process simulators in general. So I assume it would be useful for computational process synthesis in general. Big thank you to Jasper van Beten and Harry Kooijman for answering many emails from me, helping me figure out things on the simulator side of things. Yep, and thank you for listening to the talk. I hope you enjoyed it. If you're interested, please feel free to email me. And for further details on how I implemented things, please see the GitHub repo. The link's on the first slide of this talk.